For years, we all watched AI follow the same pattern. Build bigger models, throw more GPUs at them, and then extend the data centers. Intelligence followed. That era is ending because something fundamental has changed. Power stopped scaling. Right now, we are hitting hard energy limits everywhere in the world, including the United States. Texas is the clearest warning sign. Every single month, tens of gigawatts of new data center requests hit the grid, and almost none get approved. The grid is effectively sold out. And it's not just Texas. From Virginia to Ohio to the West Coast, the story is the same. The grid is full, and extending that grid takes years. When 1 gigawatt of AI compute can generate you tens of billions of dollars per year, waiting isn't an option. So AI labs stopped waiting and built their own power plants. On-site generation is exploding. Gas turbines, batteries, private power plants. As a chip design engineer, I see this as a system problem. And the only realistic way out of this is not by generating more electricity. It's by changing how computation itself is done. Subscribe to the channel and let me explain. This story starts with a Korean founder who turned down a $1 billion acquisition offer from Meta. His name is Jun Paik. He was a senior engineer at Samsung. He had a solid career, a safe trajectory, until a soccer injury took him out for months. He was stuck in bed and he started to study AI end-to-end. Models, math, systems, how software actually maps into silicon. And that's when it actually clicked. Yoon realized that the next ceiling in AI won't be algorithms. It would be power. AI would need a new way to compute, because power would no longer scale the way it used to. And if that's true, then the winning chip will not be the one with the most brute force. It's the one that can do the same work using less power. And at this point, he walked away from his role at Samsung to build something from scratch. Because at the time, brute force was everywhere. GPUs ruled AI, inference, training, everything. And that wasn't an accident. Because GPUs were built for graphics. And what is graphics? It's math. Lots of math at massive scale. Think about a 4K screen. Millions of pixels, updated dozens of times per second. Each pixel needs the same math, over and over, all done in parallel. That's exactly what GPUs are good at. Huge amounts of simple math done simultaneously. So when AI arrived, GPUs were already there. The world's best math machines. And that worked for a long time. But GPUs were never designed with energy as a constraint. They were designed to be fast, flexible, and general. That was fine when power was cheap and the grid had slack. Now, energy became the constraint. And he founded Furiosa AI with a clear promise.
So from the very beginning, our goal was to build efficient and high-performance inference chips designed to serve AI at scale in data centers and infrastructure.
They've built an NPU, Neural Processing Unit. They called it Warboy, a chip designed for just one job: running AI inference when power is tight. To understand why an NPU exists at all, you need to understand the mismatch. Neural networks run on simple operations: multiply, add, then repeat millions and then billions of times. Traditional chips were not built for that pattern. A CPU is built for complex, one-at-a-time work, branching logic, making decisions, and it's brilliant at that, but it's terribly inefficient at repetitive math. A GPU was a major step up because it can do the same operation across huge blocks of data in parallel. That's why it unlocked modern AI. But they are still general purpose. And that flexibility costs energy, because at scale, moving data around starts to dominate the power bill. An NPU gives up that generality. It's a purpose-built accelerator for one task: inference. Essentially, it's what happens after a model is trained, when it takes real input and produces real output. Every prompt you put in Gemini or ChatGPT, image and video processing, wildfire detection, all of that is inference. And at the core, inference is a very repetitive math, input data multiplied by learned weights, over and over again. So instead of building a flexible machine, you build a factory for that one operation. Inside the chip, you pack thousands of tiny cores, tiny circuits called MAC units, multiply accumulate units, and each one does exactly the same thing. Multiply two numbers and then add the result to the running total. But this is where Furiosa technology goes beyond standard neural engines. The real breakthrough is in how the data moves. Traditional chips follow the von Neumann model. Fetch data from the memory, compute, store it back, repeat. And that constant back and forth is what kills efficiency. Well, that's a problem, because in modern AI workloads, that moving data around now consumes even more energy than the computation itself. NPUs replace it with a special data flow architecture called systolic array, in order to perform large matrix multiplications without using memory at all. Here, instead of pulling data in and out of memory, data flows synchronically through the compute units like a pulse. What's beautiful, each piece of data gets reused every time as it passes through the array. In this way, those numbers stay on the chip and get reused, instead of being pulled from the memory over and over. And that makes a huge difference for power consumption. By keeping the hot data on the chip, you cut memory traffic, and that's where most of the power savings come from. That helps, but it doesn't solve the hardest part. Real inference workloads don't look so neat. Data reuse patterns shift constantly. Classic NPU designs really struggle here. Furiosa tackled this problem heads-on. Instead of forcing workloads to fit the hardware, they designed the hardware in a way that it manages to fit the workload. And we will break down how it works in a minute, and the moment it became the turning point for Furiosa's future. But before that, do you remember how all of that started? Yoon decided to learn AI end-to-end, and that single decision changed his whole life trajectory. Which brings me to this. It's January again. Most people have already made their resolutions, but the smartest one will be focusing on one skill which will matter the most in 2026: AI. Looking at how fast things are moving, 2026 is the year AI reaches maturity across real products and real jobs. Yet many people still haven't learned it. That's why I recommend you joining me for this 2-day AI workshop by Outskill. They're hosting a live training this Saturday and Sunday from 10 a.m. to 7 p.m. EST on both days. More than 10 million professionals worldwide have already attended Outskill trainings. People from marketing, finance, engineering is attending this because it isn't something specific to any industry, but now needed across every of them. And the timing matters, because right now, as a part of their New Year Upskilling Fest, you can join this training for free instead of the usual $395. This is where you learn how to build AI agents and automate workflows across tools like Sheets, Notion, and CRMs. You will also learn how to use AI to save hours weekly. If you attend both days, you will receive additional bonuses: the AI Prompt Bible, the AI Profit Roadmap, and your personalized AI Toolkit Builder. Seats are limited, so register right now through the link below or scan the QR code here. And remember to join the WhatsApp community to stay updated before the training starts. Tensors power everything from smartphone photos to black hole simulations, yet they start as a simple array of numbers. A number, like room temperature or a letter, is a zero-dimensional tensor. Line those numbers up and you get a one-dimensional tensor, like a word. Stack vectors into rows and columns and you create a two-dimensional tensor. That is a matrix. Now stack those matrices, add depth, and you arrive at a three-dimensional tensor. Example is a color image: height times width times RGB channels. That multidimensional array is what we call a tensor. Each extra dimension gives you room to pack richer structure. And to go fast, models process many tensors at once. And actually, the hard part is not computing the tensors, it's moving them into the right shape at the right time. Furiosa AI chip does something smarter. Instead of forcing the data to match the hardware adapts to the data. What happens is NPUs rearrange tensors internally, which means they fuse them, split them, reorder them, so frequently used data stays very close to compute. In vision models, nearby pixels get reused again and again. In language models, the same weights are reused across thousands of tokens. The basic idea is the neural engine reorganizes this data around reuse, which means less data movement and less energy. Think of it like a kitchen. A GPU is a very fast chef who keeps running back to the pantry, while neural engine first lays out everything on the counter and never leaves the workspace. That gap barely matters at the small scale, but at the data center scale, that difference is the energy bill. Beyond what we've discussed so far, there are a couple of more clever decisions hiding under the hood. And the first one is clock. Clock is like a heartbeat of a chip. Very important signal. And this particular chip runs at very conservative 1 GHz clock. And that's intentional. The thing is, the power chip spends on the operation scales with frequency and with square of the voltage. And lower clock means less power spent. Instead of pushing frequency, this chip scales throughput through parallelism, reuse, and locality. Which brings me to the next point. This chip features massive on-chip SRAM memory. Just imagine, each compute slice has large local memory. And across the chip, this adds up to hundreds of megabytes. It's used to store results of billions of small calculations. Why this matters is simple. This memory is pretty large, it's fast, and it's cheap because it sits right next to the compute engine. So instead of constantly streaming data in and out of external memory, chip keeps it on the die. Weights stay local. Activations get reused. Intermediate tensors never leave the chip. This is where a big part of efficiency is coming from. Then they've built a more advanced version of it, Iron Gate chip. The chip features 2 high-bandwidth memories integrated with a processor using COWS as interposer from TSMC. They manufactured the chip at 5 nanometers TSMC technology. Then hardware and software were redefined together as one system. When the chip was finally ready, they brought it to Hot Chips conference at Stanford. And this was the moment, the first time when the work stepped into the light. Furiosa AI showed their chip running Meta's Llama model. And it did so with more than twice power efficiency of high-end NVIDIA GPUs. Well, the numbers make that concrete. Furiosa AI runs at 150 watts, while high-end GPUs run at least at 350 watts. And with the latest generations, these numbers keep climbing, with the latest Blackwell pushing well beyond 1000 watts. On standard inference performance benchmarks, Furiosa demonstrated roughly 40% better performance per watt. And that difference compounds. At data center scale, this is significant. It translates into less cooling required and far lower operating cost. And of course, this didn't go unnoticed by Meta, because Meta is very serious about AI, and not just about the models. Meta also builds its own silicon. They operate at massive data center scale, and this is not slowing down. When a new AI chip shows an efficiency gap like that, they pay attention. So Meta reportedly tried to acquire Furiosa AI for almost $1 billion. Furiosa said no. What matters more is what happened next. The chip started to show up in real deployments. And that tells you just as much as the offer itself. OpenAI used the chip for a public demo in Seoul. Then LG AI Research put it through a much longer test, 7 months of evaluation on real LLM workloads. The result was clear. about 2.5 times better performance per watt compared to GPU-based solutions. And that led to a commercial deal with LG, and now they're bringing it into their data centers. And right now, Furiosa's latest chip is in mass production. That's the point where technology moved from the lab into real infrastructure. That chip and that story matters a lot because it cuts power dramatically, and this changes the economics. It actually changes where AI can run without further expanding power and cooling infrastructure. And it changes who can deploy it at scale. And chances are you've already used an NPU, a neural engine, just not in a data center. Neural engines started appearing in smartphones already a decade ago. Typically, they are built into an SoC, system on a chip. First, they were used for face recognition, photo enhancements, and voice processing. Imagine the tasks that have to run constantly on the background and have to be fast without draining the battery. Then they moved into laptops. Well, probably the most famous NPU today is Apple's neural engine. This one works quite well, not because it's unusually powerful, but because they managed to integrate it so deeply into the system. The strategy is to offload the AI tasks to neural engine, so CPU and GPU can do other work and save the battery. While Furiosa AI is applying a similar idea at the data center scale. And to be fair, they are not the only one having this idea. And this is where things start to get really interesting, because the real competition of Furiosa is not GPUs. It's other purpose-built AI chips. Like Google has its own Tensor chip, which is the most beautiful example of what an ASIC is capable of. They've managed to achieve an outstanding performance per dollar. Amazon's Trainium chip is also playing in the same arena. I will link my deep dive on these two in the description box below, so you can check it out later. Well, beyond Google, there are other players pushing custom inference chips, like Cerebras, who has a radically different wafer-scale design, a chip occupying an entire 300mm wafer. And then there is a Grok with aggressive architecture, or rather was, because they've just sold their hardware assets and the core team to NVIDIA this last December, which is actually another way of saying how strategically important inference has become. And that leaves us with very few independent companies still building serious purpose-built chips at scale. I think the next phase in AI will be defined less by who trains the biggest model, but who can train the model in the most efficient way and scale data centers fast. Actually, for hyperscalers, the speed of deployment here becomes the actual mode. At the same time, power is not getting cheaper, and the companies that survive this phase will be the ones that treat energy as a first-class design constraint. Will neural processors like Furiosa AI replace GPUs? Well, no, because GPUs will keep doing what they do the best, right? Peak raw performance for the massive training. Will they reshape inference? Very likely. These new chips will step in where efficiency matters more than raw speed, especially for AI that never turns off. Now, if you want to stay up to date with most exciting shifts in AI and technology, subscribe to the channel. And now watch this episode where I explain a new disruptive technology that will challenge both TSMC and ASML. Or watch this one, where we go inside a secret chip factory to see the future of microchips under the microscope. You will love it, and I will see you there. Ciao!